This chapter introduces Heapsort, a powerful sorting algorithm. Similar to merge sort, Heapsort has a time complexity of O of n log n. However, unlike merge sort, Heapsort is an in-place sorting algorithm, meaning it requires only a constant amount of additional memory beyond the input array. This property combines the best of merge sort's efficiency and insertion sort's simplicity. Heapsort also introduces a critical algorithm design technique, leveraging a data structure to manage information. The data structure used here is a heap, which serves as the foundation for Heapsort and is also useful for implementing priority queues. It is worth noting that the term heap in this context refers to the binary tree-based data structure, not the garbage-collected storage used in programming languages like Java or Python. Throughout this chapter, we will focus on heaps as a data structure and their applications in sorting and priority queues. A heap is a nearly complete binary tree represented as an array. Each node of the tree corresponds to an array element, making it efficient for both storage and operations. The root of the heap is located at A of 1, and the relationships between nodes are defined as follows: parent. The parent of a node at index I is located at floor of I divided by 2. Children. The left child of node I is located at 2 times I, and the right child at 2 times I plus 1. There are two main types of heaps: max heap. Every node I satisfies A of parent of I greater than or equal to A of I, ensuring the largest element is always at the root. Min heap. Every node I satisfies A of parent of I less than or equal to A of I, so the smallest element resides at the root. In Heapsort, we primarily use max heaps to facilitate sorting. Min heaps, on the other hand, are commonly used in priority queue implementations.
The two key properties of heaps are max heap property. For every non-root node I, A of parent of I greater than or equal to A of I. This ensures that the root contains the maximum value, and no child node can have a greater value than its parent. Min heap property. For every non-root node I, A of parent of I less than or equal to A of I.
This ensures the root contains the minimum value. A heap's height determines its efficiency. Since a heap is derived from a nearly complete binary tree, its height is theta of log n. Most heap operations, such as insertion and deletion, take O of log n, making it an efficient structure for managing sorted data. Several basic procedures enable efficient heap operations. Max heapify ensures that a node and its subtree satisfy the max heap property. This operation has a time complexity of O of log n. Build max heap converts an unordered array into a max heap in linear time, O of n. Heapsort utilizes max heaps to sort an array in place, with a time complexity of O of n log n. Priority queue operations includes max heap insert, max heap extract max, and max heap increase key, allowing heaps to efficiently manage dynamic datasets. These operations form the basis of Heapsort and provide the foundation for using heaps in advanced applications like priority queues. The max heapify procedure is the cornerstone of maintaining the max heap property. When a node I violates the max heap property, meaning A of I is smaller than one or both of its children, the following steps restore order: compare A of I with its children to identify the largest value. If a child node has a larger value, swap A of I with the largest child. Recursively apply max heapify to the affected subtree until the max heap property is restored. This recursive process ensures the heap structure remains valid. The time complexity of max heapify is O of log n, corresponding to the height of the heap. It efficiently repairs violations with minimal computational overhead, making it a fundamental operation for both Heapsort and priority queues. The build max heap procedure transforms an unordered array into a max heap. This process is carried out in a bottom-up manner, starting from the lowest level of the tree where the leaves reside. The build max heap procedure initializes by setting the heap size to the length of the array and then iteratively applies max heapify to each non-leaf node, moving upward toward the root. The procedure operates as follows: start with the subarray consisting of the leaves, which are already one-element max heaps. Then, for each internal node, apply max heapify to ensure it satisfies the max heap property. This bottom-up approach ensures that each subtree becomes a max heap before the next level is processed. By the time the root is reached, the entire array has been converted into a max heap. The time complexity of build max heap is O of n, which may seem counterintuitive given the O of log n complexity of max heapify. However, the analysis considers that most nodes in the heap are at lower levels and have smaller heights, leading to an overall linear runtime. The Heapsort algorithm utilizes the max heap property to sort an array in place. It begins by calling build max heap to create a max heap from the input array. The largest element, stored at the root, is then swapped with the last element in the heap, effectively placing it in its correct sorted position. Next, the heap size is reduced by 1, excluding the sorted element, and max heapify is called on the root to restore the max heap property. This process repeats until the heap size is reduced to 1, leaving the array sorted in ascending order. Heapsort is efficient because it leverages the structure of a max heap to repeatedly extract the largest element and place it in its correct position. The time complexity of heapsort is O of n log n, which consists of the linear time required to build the max heap and the logarithmic time for each of the n-1 extractions. The time complexity of heapsort can be broken down into its constituent parts. First, the build max heap operation, which constructs the initial max heap, runs in O of n time. Then, for each of the n-1 iterations, the largest element is extracted, and max heapify is applied to restore the heap. Each max heapify call operates in O of log n time. When combined, the total time complexity of heapsort becomes O of n log n. This makes heapsort asymptotically optimal among comparison-based sorting algorithms. Its in-place nature, requiring only constant extra space, also adds to its efficiency. Despite these advantages, practical implementations often favor quicksort due to its superior performance in average case scenarios. Priority queues are a versatile data structure that manage a set of elements, each with an associated key. In a max priority queue, the key represents the priority, and the highest priority element can be accessed in constant time. The operations supported by a max priority queue include insert, which adds a new element to the set, maximum, which retrieves the element with the highest key, extract max, which removes and returns the element with the highest key, and increase key, which increases the key value of an existing element. Max priority queues are commonly implemented using max heaps. For example, the root of a max heap contains the element with the highest priority, which can be accessed in constant time. Operations such as extract max and increase key maintain the max heap property and run in O of log n time. Priority queues have diverse applications, including job scheduling, where tasks with higher priority are executed first, and event-driven simulations, where events are processed in order of their occurrence. The implementation of priority queues using heaps requires careful mapping between application objects and heap elements. Each element in the heap corresponds to an object in the application, and additional information, such as handles, is often used to establish this correspondence. Handles are stored in the objects and heap elements to facilitate the mapping between them. Alternatively, a separate mapping structure, such as a hash table, can be used to track the relationship between application objects and heap indices. This approach keeps the mapping entirely within the priority queue implementation, simplifying the application logic. The operations of a max priority queue, such as maximum, extract max, and increase key, are implemented efficiently using max heaps. For example, the maximum operation retrieves the root element in constant time, while extract max and increase key run in O of log n time, ensuring efficient priority management. When implementing priority queues with heaps, special care must be taken to handle objects and their corresponding keys. In many applications, each object in the priority queue is associated with a unique key that determines its position in the heap. To map between application objects and heap elements, two common approaches are used. The first approach involves using handles, which store additional metadata within each object or heap element, allowing efficient mapping. Handles are designed to be opaque, maintaining a clear separation between the application logic and the priority queue implementation. The second approach uses a separate data structure, such as a hash table, to map objects to their indices in the heap. This method simplifies the objects themselves but adds overhead to maintain the mapping. Operations such as extract max and increase key require updating these mappings whenever heap elements are moved. This ensures that both the priority queue and the application maintain consistency. The overhead for mapping is typically O of 1 per operation when using a well-designed hash table, making it a practical choice for most applications. Priority queues have numerous real-world and computational applications. In job scheduling, priority queues manage tasks by priority, ensuring that higher priority jobs are executed before lower priority ones. Similarly, in event-driven simulations, a min priority queue is used to process events in chronological order, with the event having the earliest timestamp being handled first. In graph algorithms, priority queues play a critical role. For example, Dijkstra's shortest path algorithm uses a min priority queue to repeatedly extract the vertex with the smallest tentative distance, enabling efficient path finding. Another notable use is in data compression algorithms like Huffman coding, where priority queues help construct optimal prefix trees. These examples highlight the versatility and importance of priority queues across a wide range of domains. Several advanced variants and improvements to heaps and priority queues have been developed to optimize specific operations. For instance, DRE heaps generalize binary heaps by allowing each node to have D children, which can reduce the height of the heap and improve the performance of certain operations. Fibonacci heaps are another powerful variant, offering O of 1 amortized time for operations like insert and decrease key, making them highly efficient for graph algorithms such as Dijkstra''s. Other notable variants include Brodel queues, which guarantee worst-case O of 1 time for key operations, and radix heaps, which are particularly efficient for monotone priority queues in Dijkstra's algorithm. These improvements demonstrate how specialized data structures can achieve better time bounds for specific applications, extending the utility of heaps and priority queues. A detailed analysis of Heapsort reveals several key insights and optimizations. In the best case, the number of element moves during Heapsort is approximately n divided by 2 times log n, while the average number of moves is close to n times log n. These results highlight the efficiency of Heapsort compared to other sorting algorithms. Optimizations for specific use cases, such as integer keys or monotone sequences of operations, have further improved the performance of heaps and priority queues. For example, in scenarios where the sequence of extract min operations is monotone, specialized structures like radix heaps achieve superior performance. Such optimizations underscore the ongoing research and development in improving the efficiency of heaps and their related algorithms. In conclusion, Heapsort is a highly efficient sorting algorithm with a time complexity of O of n log n. Its in-place nature makes it an excellent choice for memory-constrained applications. Beyond sorting, heaps form the foundation for efficient priority queue implementations, enabling operations such as insert, extract max, and decrease key to run in logarithmic time. Moreover, heaps and priority queues are indispensable tools in computer science, supporting a wide range of applications from graph algorithms and event simulation to job scheduling and data compression. Continued research into variants like Fibonacci heaps and Brodel queues has further expanded their utility, ensuring that heaps remain a cornerstone of efficient algorithm design. Heapsort and related structures exemplify how fundamental algorithms and data structures can have profound and lasting impacts on computational efficiency.